Now we will do the second part of the chapter wave optics, the concluding part of this chapter, wave optics. We will begin with a very important topic that is known as Higgins principle. Higgins principle. First of all, we have seen in the last class that light is an electromagnetic wave and therefore it has wave-like nature. Now what happens is that suppose this is a point source of light. If you draw a circle, if you draw a surface which is at a fixed distance from the source, so this surface is called a wave front. That means what I'm basically trying to say is that this radius is a given radius with respect to point S as center. This is called a wave front. So a wave front is a surface in which at any 2 points the disturbance is in the same phase. So if you take any 2 points on the wave front, the disturbance will be in the same phase. Another thing is that the direction of propagation of the wave will always be perpendicular to the wave front. So if you say that this is your wave front, then the tangent to the wave front and the direction of propagation, they will always be perpendicular. And this is in fact a rule that for any point source, the wavefront will always be spherical, like the one which I have drawn over here. Now what exactly is Higgins principle? Let us say you have located a wavefront, and on this wavefront there are 3 points S1, S2 and S3, and like I told you, these 3 points are in the same phase. According to Higgins principle, if you draw arcs whose radius is equal to Vt, V is the speed of light and T is the time of travel. So if you draw arcs whose radius is Vt and the centers of these arcs will be at S1, S2 and S3, then the envelope of these arcs, something like this, this envelope will give you the new position of the wavefront at time t. So let us say you are interested in knowing the new position of the wavefront at time t. So it will be the envelope of all these arcs, and these arcs are called secondary wavelets. Now what I mean to say is that you first located a wavefront. On the wavefront you have 3 points S1, S2, S3. With S1, S2 and S3 as center, you drew secondary wavelets. Each wavelet has radius Vt, where V is the speed of light and T is the time. And the envelope of all these wavelets gives the new position of the wavefront at the time t. And these secondary wavelets are all of fixed radius, and the radius will be V into T. So this is known as Higgins principle. Now how do we apply Higgins principle? You will be very surprised to know that Higgins principle is actually the basis for the proof of laws of reflection and laws of refraction. Now let us see how. Suppose there is a transparent medium. Suppose there is a transparent medium and AB is the incident wave front. So this is a transparent medium. You could say, suppose it's a plane mirror, something like that. AB is the incident wave front This is the incident wave, it is perpendicular to the wavefront. If you produce this, then it will reach the mirror at point C. So you could say that the incident wave is the one shown by this arrow, and after a time t, it will reach the mirror, and the point where it reaches the mirror is C, and this distance BC is equal to Vt. Now what you do is, with A as center and Vt as radius, you draw an arc. So this arc becomes your secondary wavelet. So with A as center and radius Vt, you draw an arc. This arc is secondary wavelet, and from C you draw a tangent to this secondary wavelet. As a result, if you draw the radius, let us call it AD, so AD will be perpendicular to CD. Now, I told you that AB is the incident wavefront, and by using the Higgins principle, we drew a secondary wavelet, and that helped us to draw the reflected wavefront, which is CD. So CD is the reflected wavefront, which means that you could say that AD is the reflected wave, and just like BC is the incident wave. So if I draw a line like this is the angle of incidence, and if I draw a normal over here, this is the angle of reflection. If this is the angle of incidence, then this should be 90 minus I, which means this angle is I, angle BAC is I. Similarly, if this is R, this is 90 minus R, so therefore this angle is R, which means angle DCA is R. Now let us consider triangle ADC and ABC. In these two triangles, first of all, AC is common, number one. Number two, angle ADC equal to angle ABC equal to 90 degree. Angle ADC equal to angle ABC equal to 90 degree. Number three, AD is equal to BC is equal to VT. So in triangle ADC and ABC, AC is common, angle ADC equal to angle ABC equal to 90 degree, AD equal to BC equal to VT. So right angle hypotenuse side, that means ADC is congruent to ABC. Now if ADC is congruent to ABC, due to congruency we can say that angle BAC should be equal to angle DCA. Thanks to congruency, angle BAC should be equal to angle DCA. But angle BAC is I and angle DCA is R, which means that angle of incidence will be equal to angle of reflection. And you know very well that this is also called the law of reflection. That means angle of incidence equal to angle of reflection. Another thing is that in this diagram, the incident wave, reflected wave and normals are all drawn on the plane of the board. So the incident wave, reflected wave and these two normals are all drawn on the plane of the board, which basically tells us that the incident wave, reflected wave and normal lie on the same plane. So these are the two very, very well-known laws of reflection and their proof using Higgins principle. Now let us have a look at proof of laws of refraction. Now, in proof of laws of refraction, again AB is the incident wave front. So, at the time of consideration, A is already at the boundary of the two media, B is about to reach the boundary of the two media, and let us say speed of light in this medium is V1, speed of light in this medium is V2. So, the distance from B to C will be, let us say, V1 into time. So what we will do is, taking A as center and radius V2t, we will draw a secondary wavelet. So this is a secondary wavelet whose center is at A and radius is V2t. Then from C, we will draw a tangent to this secondary wavelet. So the tangent will be CD. So thanks to the Higgins construction, AB is the incident wave front and CD is the refracted wave front. So AB is the incident wave front and CD is the refracted wave front. Now this is the normal. So if this is the angle of incidence I, then this will be 90 minus I. So automatically this will be I. And again, because this is the normal, this angle of refraction R, so this is 90 minus R, so this angle will be R. Now if you look at triangle ABC, sin I will be V1t by AC, and if you look at triangle ACD, sin R will be V2t by AC. So therefore we get sin I by sin R is equal to V1 by V2. If you know that this is the very well known Snell's law of refraction, which says that for a pair of media, the refractive index, which is equal to speed of light in the first medium by speed of light in the second medium, is equal to sin I by sin R. So this is the proof of the well known laws of refraction. Secondly, in this diagram, the incident wave, the refracted wave and the normal, they are all on the plane of the board. So we can say that the incident wave, refracted wave and normal lie on the same plane. So this is the proof of the second law of refraction. Now we come to the next part of the chapter, that is known as polarization. You know that light can propagate in infinite directions. So light is an electromagnetic wave which consists of two mutually perpendicular electric and magnetic fields. For convenience, let us consider the electric field vector associated with light. Let this be called as E. So it can vibrate in any direction perpendicular to the propagation. So suppose light is propagating like this, then you can have infinite directions perpendicular to the plane of propagation, and all of them can be the direction of the electric field vector associated with the light. Now, for our convenience, what we will do is, it is very cumbersome to consider so many possible directions of electric field vector. So for our convenience, what we will do, if this is the direction of propagation, then we will resolve all electric field vector into two directions, one perpendicular to the direction of propagation in this manner, and the other, this one is on the plane of the board and this dot is in the perpendicular to the plane of the board. Once again, the electric field vector associated with light can have infinite directions. For our convenience, we will consider two directions. One on the plane of the board, that is represented by this double arrow, and secondly perpendicular to the plane of the board, that is represented by this dot. So for our convenience, we will consider these two directions as the directions of the electric field vector associated with light. Now, what happens is that there are some devices called Polaroids. Now, what does a Polaroid do? Every Polaroid has an axis of transmission. Every Polaroid has an axis of transmission. So, if you pass light through a Polaroid, then only that component of electric field vector which is parallel to the axis of transmission will be transmitted, and you can see that these black dots are not present in the transmitted light. So a Polaroid's job is to transmit all those components which are parallel to its own axis of transmission and to nullify all the components which are not along the axis of transmission or which are perpendicular to the axis of transmission. So these dark dots are completely absent in the light which is transmitted. This is known as unpolarized light, and this one is known as polarized light. So the definition of polarized light, we could say that the vibrations of the electric field vector occur perpendicular to the direction of propagation and are confined to a single direction. So only this direction is possible, any other direction is not possible. Whereas in case of unpolarized light, the vibrations of the electric field vector can occur symmetrically in all possible directions perpendicular to the plane of propagation. So that is the difference between unpolarized light and polarized light. Now this device, in this particular experiment, we refer to this device as the polarizer. Now let us say that we place another Polaroid in front of the polarized light so that the transmission axis has been rotated by theta. So an identical Polaroid whose transmission axis has been turned by an angle theta. Now, if the intensity of the polarized light is I0, then the intensity of light transmitted by the second Polaroid is equal to I0 cos square theta. This is known as law of Malus or Malus's law. So once again, what is Malus's law? that the polarized light coming out of the polarizer, when it is passed through another polaroid whose transmission axis is inclined at an angle theta to that of the first polaroid, then the intensity transmitted by the second polaroid is I0 into cos square theta. And by the way, this second polaroid, we refer to it as the analyzer. So this is known as Malus's law, and it's an important law which helps us to analyze the intensity of transmitted light by the second polaroid. Now we come to the second important law of this chapter. This is known as Brewster's law. Now, according to Brewster, suppose this is the incident ray. We are talking about refraction. Suppose this is the incident ray, and the incident ray is unpolarized light. This is unpolarized, and this is the refracted ray. This is also unpolarized. Now, for a certain angle of incidence, that is IP, IP is called polarizing angle. According to Brewster, for a certain angle of incidence that is equal to polarizing angle, the reflected wave will be completely polarized. For example, you can see that this is unpolarized, but the vibrations on the board are completely missing in the reflected wave. So when the angle of incidence is equal to polarizing angle, that time the reflected wave is completely polarized. So the exact statement of Brewster's law is that for a particular angle of incidence, the reflected wave is completely polarized with vibrations perpendicular to the plane of incidence. So you can see these vibrations are only in the plane perpendicular to the plane of incidence. Now, how do you define polarizing angle? According to Brewster, he said that the tan of polarizing angle is equal to refractive index, but suppose angle of refraction is R, you know that refractive index is sin I by sin R, so that is sin IP by cos IP. So if you write this as sin IP, then you will get sin R is equal to cos IP, which means IP and R are perpendicular to each other. So according to Brewster's law, for polarizing angle of incidence, the reflected ray will be completely polarized. Secondly, the reflected wave and the refracted wave, they will be perpendicular to each other. So that brings us to an end of Brewster's law, and it also brings us to an end of wave optics.